All right, class, let me try another one. How about chapter 21, number 58 here. It says in a PV diagram for an ideal gas, one isotherm curve and one is adiabatic curve passes through each point. I think what they're trying to say, I'm not sure if I like the wording the author uses there, but in a PV diagram, here's the point that hopefully you saw, and I tried to describe that in a PV diagram, the isotherm is a hyperbola, and the adiabatic, and it depends which point you want to reference, is a little steeper, so maybe I'll just do, they have the same point at what you might call the final volume, if you called this the initial, and then of course this would have to have a different initial. But the adiabatic here should be this steeper one, and that's why just drawing a PV diagram, it's kind of hard to tell which one is, or if it's an adiabatic, or if it's a constant temperature, which is an isotherm. You can't really eyeball it. And now, if you put them side by side, like I've just done, maybe you can, but they both have this steepness to them. So if they expanded, so they'd be starting at a different initial volume, although maybe the same initial pressure, and then as they expand, the adiabatic would be steeper than the isotherm, and then they would make some point right here. And I guess if it continued on, it would be steeper here and continue on something like that. Okay. So there is some point where they cross. So at some point they have the same pressure and volume, but they don't have the same slope. They have a different steepness to it. And that's kind of the clue here. You probably remember from your calculus class that if you have some, y as a function of x equals blah, 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 blah. If you took the derivative of y with respect to x, that is then the slope. So in this case, I would be looking for dP dV. How does the pressure change with volume? That would be the slope. So let me start with the isotherm. The isotherm says this, that PV equals to nRT. And so if I go ahead and I take the derivative here of the whole equation, maybe with respect to volume, and so that I can get something that looks like this, I would have the first times the derivative of the second, and the second times the derivative of the first. Okay, that's a good sign right there, because there it is. There's the dP dV. That is the slope. That's what I'm hunting for. Okay, and so we have the pressure and volume changing. Now, the other side of this equation has nothing that changes. I mean, during an isotherm, the pressure and volume change. That's why I had to, do the product rule to take the derivative here. But the temperature doesn't, and so that's a constant, and derivative of a constant is 0. All right, so if I rearrange this, and of course noting that dV dt is just 1, I could move the pressure to the other side, so that'd be minus P. Then I would divide by V, and I would have then dP dV, and so this is the slope. So the slope of the isotherm would be some value that would, of course, depend where you are on the graph. This is the isotherm. But if you took the current pressure at that reading and divided it by the current volume, and of course took the negative of it, that would be the slope. So that's the slope of an isotherm. Now, an adiabatic is a little different function. The adiabatic is pressure times volume raised to a power of gamma is equal to some constant value. Now, that constant value would depend on the number of moles and some other factors. But the point is that we have as much as we need right here because we have the relationship of how pressure and volume change. And it's a little different than the isotherm. So if we take the whole equation again and take the derivative with respect to volume, we would have the first times the derivative of the second. And so this would be gamma, and then volume gamma minus 1, because it's a power function. If you remember, and when you take a derivative of a power function, you bring down the exponent, so there's the gamma, and then you reduce the exponent by 1. Okay, so there's first times the derivative of the second. Then the second, so volume to a power of gamma, times the derivative of the first, dp dv. Okay, and again, there's what we're hunting for. What is dp dv? That is the slope. And then again, the right-hand side's pretty easy because it's a constant. So the derivative of a constant is just 0. Okay, so now if we rearrange this, and maybe I'll do a couple steps here. I'll leave volume to a power of gamma dp dv. And when I bring this all over, there's the negative. Why don't I write it this way? I'll put the gamma first, okay? Then I'll put the volume, and I'll write it, I guess, two ways, to a power of gamma, and then also to a power of -1, and then times p. Because then when I bring this volume to a power of gamma to the other side, so, well, I won't even bring it to the other side. I'll just cross it off right there. Yeah. I get what I'm looking for. This is dp dv. This is the slope of the adiabatic process. And it looks like if I just write the factor of gamma first and then write the negative and then the p, and then volume to a -1 would be this. This right here, this negative p dv, that's that thing right there. That is the slope of the isothermal process. So the slope of this adiabatic is gamma multiplied by the slope of the isotherm. And I think that was the question. It says, yeah, prove that the slope of the adiabatic, so this is the slope of the adiabatic, maybe I'll just put slope q equals 0, then equals gamma times, and this right here would be slope of the isotherm. So I'll go temperature equals constant. Okay? So the slope of the function with temperature equals a constant. If you multiply it by a factor of gamma, you get the slope of the adiabatic. Yeah, nice.